Hi guys, it's Emma Acuña of Bachelor of Science in Civil Engineering 1-3, and let's talk about thermochemistry. In here, we'll talk about the first law of thermodynamics, enthalpies of reaction, calorimetry, Hess law, enthalpies of formation, foods and fuels. Let us first define thermodynamics. Thermodynamics is the science of the relationship between heat, work, temperature, and energy. Or in other words, it deals with the transfer of energy from one place to another or from one form to another. One portion of thermodynamics is thermochemistry, which is the study of heat energy, which is associated with chemical reactions and or phase changes. Energy is transferred to an object in order to move it in the form of force. This amount of energy transferred is called work or work done, and the relationship of work and energy are directly proportional to each other. Here, the formula for work is equal to delta E, which is the energy transferred, and also work is equal to force times distance. We now have here a sample problem where we are asked to solve for the work done. We'll use the formula work is equal to force times distance. Our force is 200 Newton and our distance is 8.0 meters. Substituting values to our formula, we now have work is equal to 200 Newton times 8.0 meters. Our work is 1,600 joules. We can easily differentiate kinetic and potential energy by defining kinetic energy as the energy of an object in motion and the potential energy as the stored energy. Kinetic energy has the formula of Ke is equal to 1 half times mass times volume squared, and potential energy has the formula of Pe is equal to mass times the gravitational field strength times the height. This representation shows the relationship between kinetic and potential energy. We can observe that they both have an opposite relationship because as the potential energy increases, the kinetic energy decreases. And as the kinetic energy increases, the potential energy decreases. Energy or work has an SI unit of joules, which is named after James Prescott Joule, which is an English physicist. 1 joule is equal to 1 kilogram per meter squared per second squared. A calorie is a unit for measuring heat equal to the amount of heat required to raise the temperature of 1 gram of water to 1 degree Celsius. 1 calorie is equal to 4.184 joules. System is the study piece or material, which is light blue in this picture. Boundary is what separates the system and the surroundings, though it normally doesn't have a physical value. Surroundings is everything around the system, and all this set is called the universe. We have three types of system, which are open, closed, and isolated system. First, we have the open system, where mass as well as energy can transfer across the boundary. Next, we have the closed system, in which there is no mass transfer across the system boundary, but energy in form of heat and work can cross the boundary. Lastly, the isolated system. In here, the mass and energy is fixed and there will be no transfer of mass and energy in the system. We have here an example of the three types of system. The example of an open system here is a boiling water on a saucepan without a lid on it. As you can see, because it doesn't have a lid, the exchange of energy and matter can happen. An example of the closed system is this heated pan with the lid. Due to it having a lid, transfer of mass is not allowed and only energy can transfer. Our example of an isolated system is a thermoflask because it is perfectly insulated closed vessel that doesn't allow the transfer of mass and energy across the boundary. Work is the transfer of energy when a force acts through a distance. A force is an influence that can change the motion of an object. The formula for work is equal to force times distance. Another way an energy can transfer is through heat. Heat is defined as a transfer of thermal energy from a system to its surroundings or from one object to another. Heat takes place as a result of difference in temperature. If two objects that have different temperatures are placed in contact with one another, energy will flow from the hotter object to the cooler one until thermal equilibrium is reached. Now let's try to answer a sample problem. To answer letter A is as the ball is raised into the ground, its potential energy increases. To answer letter B, let's use the equation work is equal to force multiplied by the distance. We will also use force is equal to mass times gravity for the force that is due to gravity. To calculate for the quantity of work, our formula will now be work is equal to mass times gravity times distance. Let's substitute our values, then our answer will be 68 joules. Next, let's answer question C. Let's use the equation kinetic energy is equal to 1 half mv squared, assuming that the kinetic energy before the ball hits the ground is the work done in part B. Derive the formula to solve for V. We'll have V squared is equal to 2ek over m. Substitute all values to the formula. We now have the answer 6.73 meter per second, which is the ball speed before it hits the ground. The first law of thermodynamics states that energy cannot be created nor destroyed, it can only be transferred from one place to another. Internal energy is the sum of all the molecular kinetic and potential charges. It is also a quantity that is directly proportional to the temperature of a sample. The change in internal energy can be solved by subtracting Q and W, where Q is the heat added to the system and W is the work done by the system. With regards to relating heat and work to changes of internal energy, we have here an example. When a hot plate is turned on, the system gains heat from the surroundings. Both the temperature and internal energy will then increase, resulting to E being positive. When the hot plate is turned off, the water loses heat to its surroundings, resulting to E being negative. Let's try to answer this sample exercise. After analyzing the given problem, we can now determine the signs of Q and W. Let's then use a formula for calculating delta E, which is delta E is equals to Q plus W, given that the system absorbed 770 joules of heat from the surroundings, or Q is positive. W is negative because the work is done by the system by delivering 520 joules of work in the surroundings. Using the formula, let's substitute all the values and we'll have the answer 250 joules. Delta is positive, so we can say that the system gained 250 joules. An exothermic process is a reaction that gives off heat to the surroundings. An example is when a fire is lit and it gives off heat to the surroundings. An endothermic reaction takes in energy from its surroundings, like when the ice melts by taking heat around it. Remember that exo means giving out and endo means taking in. So, what is a state function? In simple terms, a state function is measurable quantity about matter as it does nothing. Examples are internal energy, entropy, and free energy. Enthalpy has the mathematical value of H is equal to E, which is the internal energy, plus PV, which is pressure multiplied by volume. Enthalpy is presented by the capital letter H. We have here a simple problem that asks us to calculate for the enthalpy if our pressure is 40 atmosphere, our internal energy is 38 joules, and our volume is 5.4 liters. Using the formula H is equal to E plus PV, substitute our values and we have the answer 254 joules. Pressure work volume is done whenever we have a volume change against an external constant pressure. We have an expansion when there is an increase in volume and compression when there is a decrease in volume. We can use the formula work is equal to negative P delta V, where P is the pressure and delta V is the final minus the initial volume. Work here is negative because it is being done in the surroundings. During a compression, work here is going to be positive because work is being done on the system. In this sample exercise, we are going to use the formula work is equal to negative P delta V. Let's first compute for delta V. Final volume is 1.45 liters minus the initial volume 0.225 liters. We have the delta V, which is 1.225 liters. Substituting values to our formula for work, we have negative 1.35 atmosphere times 1.225 liters. We have negative 1.65375 liters per atmosphere. The problem wants the answer to be expressed in joules, so let's convert negative 1.65375 to joules. Negative 1.65375 liters per atmosphere multiplied by 101.3 joules per 1 liter per ATM. We now have the answer negative 167.52 joules as the work done. The enthalpy of reaction, denoted by delta H, Rxn, is the difference in enthalpy between products and reactants. Delta H Rxn is negative when we have an exothermic reaction and positive when we have an endothermic reaction taking place. When a process or reaction is reversed, the sign of delta H also changes. In the example we have here, we can observe how reversing a reaction affects the sign of delta H. To answer this sample problem, let us first calculate the number of moles using this formula. Substituting values will have a resulting value of 0.088 moles. By stoichiometry of the reaction, we can say that 8.62 kilojoules is the amount of heat released for the given amount of hydrogen peroxide. Calorimetry is used to measure amounts of heat transferred to or from a substance. A calorimeter is a device used in calorimetry. Let's differentiate heat capacity, specific heat, and the molar heat capacity. Heat capacity is equal to heat divided by the change in temperature. The unit for heat capacity is joules per degree Celsius. It is a property that depends on the amount of material. Specific heat is equal to heat divided by the mass times the change in temperature. The unit is joules per gram per degree Celsius. Specific heat does not depend on the mass. The molar heat capacity is equal to heat divided by the moles times the change in temperature. The molar heat capacity does not depend on the mass also. To answer this problem, we'll use the equation heat is equal to mc delta T. Let us first solve for the value of delta T. Final temperature, which is 95 degrees Celsius, minus the initial temperature, which is 12 degrees Celsius. We now have the value of delta T, which is 83 degrees Celsius. Using the first equation, let's now substitute 320 grams as the mass, 4.18 joules per grams per degree Celsius as the specific heat, and 83 as our delta T. The quantity of heat required to raise the temperature of water from 12 degrees Celsius to 95 degrees Celsius is 111,020 joules. Let's try another problem. In here, we'll also use the formula heat is equal to mc delta T to determine the quantity of heat. Let's calculate first the value of delta T. 90 degrees minus 10 degrees Celsius, or delta T is 80 degrees Celsius. We can now substitute values to our formula and our Q will be 167,360 joules. Constant pressure calorimetry is the way we can measure delta H for a chemical reaction. And here, we first need to calculate for the heat of the solution by using the formula Q solution is equal to mass of the solution times the specific heat of the solution times delta T. Once we know the amount of heat that is absorbed by the solution from the reactants as they get converted into products, we can now find the heat of the reaction. All of the heat that was absorbed by the solution is the amount of heat that's released by the reactants as they turn into products. So to find the heat for the reaction, it's simply going to be the negative of Q solution. We have to calculate heat for the reaction system. Let's use the equation heat of solution is equals to mc delta T, or mass times specific heat times the change in temperature. Substituting values will have 50 grams times 4.18 joules per grams per degree Celsius times 1.68 degrees Celsius. I forgot to type delta T. Apologies. Our Q solution is 351 joules. As I said earlier, our Q reaction is simply the negative of our Q solution. So the answer will be negative 351 joules. Constant volume calorimetry is a way we can measure the internal energy change, or delta E, for chemical reactions. In order to have a reaction taking place at a constant volume, a bomb calorimeter was normally used. In order to calculate the amount of heat absorbed by the calorimeter when burning a sample, we first need to know delta T and the heat capacity of the calorimeter. We now have this equation where Qcal, or the heat of the calorimeter, is equal to Ccal, or the specific heat of the calorimeter, times delta T. And if we want to know the heat of the reaction, it's just the negative of our Qcal. In this sample problem, we need to find delta E reaction. We must first solve for Qcal using the formula Qcal is equals to Ccal times delta T. The heat capacity of the calorimeter is given, which is 5.01 kilojoules per degree Celsius. Substituting values to our formula, we have 5.01 kilojoules per degree Celsius multiplied by 31.20 degrees Celsius minus 23.50 degrees Celsius. Our heat of calorimeter will be 38.6 kilojoules. We can now solve for delta E reaction, knowing that it is equal to our heat of reaction, which is also equal to negative of our Qcal. So our heat of reaction is negative 38.6 kilojoules. The idea for Hess's law is that the change in an overall process from the initial state to the final state is sometimes difficult to do by itself. Breaking it up into steps and knowing delta H of each process will also lead you in knowing the overall change by adding all delta H. Hess's law was first introduced by Germain Henry Hess, which is a chemist. Here we have a sample problem. Let's look at this sample problem. For the first reaction, we have the combustion of 2 moles of ethane to produce carbon dioxide and water. The enthalpy change for this reaction is negative 3,120 kilojoules. In the second reaction, we have the combustion of 2 moles of hydrogen to produce 2 moles of water. The enthalpy change for this reaction is negative 572 kilojoules. In the last reaction, we have the combustion of 1 mole of ethane to produce carbon dioxide and water. The enthalpy change for this reaction is negative 1,411 kilojoules. Since in our final equation, we only have 1 mole of ethane, we need to divide all the equation in the first reaction by 2. Since the equations was halved, our enthalpy change for the first reaction is now negative 1,560 kilojoules. On the second reaction, our hydrogen is in the reactants. However, in our final equation, our hydrogen is in the products. We also have 2 moles of hydrogen in the second equation and 1 mole on the final. So, we need to reverse the equation and divide the coefficients by 2. We also need to do this on the enthalpy change. So we now have positive 286 kilojoules on the third equation. We have 1 mole of ethane in the reactants, but on the final equation, we have 1 mole of ethane in the reactants. We need to reverse the equation. We also need to do this in our enthalpy change, giving us positive 1,411 kilojoules. Let's form our final equation by canceling out the same things on the opposite sides. Last step is to add all the enthalpy change, and all three reactions will give us an enthalpy change of positive 137 kilojoules. Carbon dioxide decomposes to carbon and oxygen, and the enthalpy change in this reaction is 393.5 kilojoules per mole. Our next reaction is methane, decomposes to carbon and hydrogen with an enthalpy change of 74.6 kilojoules per mole. Lastly, carbon reacts with hydrogen and oxygen to produce acetic acid, and the enthalpy change for this reaction is negative 484.3 kilojoules per mole. We need to cancel out products and reactants which appears to both sides of the equation, giving us the equation carbon dioxide reacts with methane to produce acetic acid. In order to get the enthalpy change of this equation, we'll add all the enthalpy change of our three reactions, 393.5 plus 74.6 plus 484.3 is equals to negative 16.2 kilojoules per mole. Enthalpy of formation is the enthalpy that goes into or is released during the formation of 1 mole of a compound from its basic elements with all of the substances in their standard states. The symbol used is delta H F degrees, where F stands for formation and degree tells you that it is in standard condition. The standard enthalpy of reaction can be calculated by summing the standard enthalpies of formation of the reactants and subtracting the value from the sum of the standard enthalpies of formation of the products. We can mathematically express this as the equation you can see here. Here we have an example. We need to calculate the standard enthalpy of reaction for the combustion of methane. First, let's look for the standard enthalpies of formation for each of the reactants and products involved in the reaction. Here are the data needed. Sum up the standard enthalpies of formation of our products and our reactants. It is said here that the enthalpy of formation for oxygen is 0 kilojoules per mole because it exists in standard condition. Substitute the resulting sum to our equation and we'll have our standard enthalpy of reaction, which is negative 887 kilojoules per mole. So let's answer the sample problem. We are asked to calculate for the enthalpy change for the combustion of 1 mole of glucose to carbon dioxide and water. Let us first prepare a balanced chemical reaction, then let's look for the standard enthalpies of formation for the reactants and the products involved in the reaction. Substitute values in our equation and we'll get our enthalpy change, which is negative 2,816 kilojoules per mole. We need to consume foods in order to have enough energy to go through our day. Most chemical reactions used for the production of heat are combustion reactions. The energy released when 1 gram of any substance is combusted is the fuel value of the substance, which can be measured by calorimetry. Most of the energy our body needs comes from carbohydrates and fats, and the average fuel value of carbohydrates is 17 kilojoules per grams. Next, fats are well suited to serve as the body's energy reserve because first, fats are insoluble in water, which facilitates storage in the body, and second, they produce more energy per gram, which makes them efficient energy source on mass basis. The average fuel value of fats is 38 kilojoules per grams. It is said that the greater the percentage of hydrogen and carbon in a fuel, the higher its fuel value is. Coal, petroleum, and natural gas, which are fossil fuels, are the world's most sources of energy. The natural gas consists of hydrocarbons, petroleum consists of hydrocarbons and other organic compounds, and coal contains hydrocarbons of high molecular weight, as well as sulfur, oxygen, and nitrogen. I will now end my presentation here. Thank you so much.